Good morning. This morning we're going to do 14.4 Log and Anti-Lock Amplifiers. They say log and anti-lock amplifiers are used in applications that require compression of analog input data, linearization of transducers that have exponential outputs, and anti-lock multiplication and division. They are often used in high-frequency communication systems, including fiber optics for processing wide dynamic range signals. All right. Up till now, a lot of the amplifiers, they got a linear output, all right. This thing will have a logarithmic output, all right. Sometimes you've got transducers that also give you a lot of logarithmic output. You want to convert it to a linear output, and that's where we're going to use these anti-lock, log and anti-lock amplifiers. All right, if we have a look at this, here we got a curve. Where did you use this curve previously in your course? That is a P-N junction, a diode. The diode characteristic curve, forward bias diode characteristic curve will basically give us this, all right. But the logarithmic part of the curve will be basically up to 0.7 volts. That means when we go past 0.7 volts, what happens? Then it goes straight and it's not logarithmic anymore. That means the logarithmic part is basically up to around about 0.7 volts for a silicon diode or a silicon P-N junction. All right, here they give us the forward voltage, the forward current. It's approximately equal to IR, stands for my reverse or my leakage current. E to the power Q times V, VF stands for the forward voltage divided by K times my absolute temperature, all right. That is the basic equation for my forward current. Let's just look at the key elements that we're going to talk about here. They state the key elements in a log amplifier is a device that exhibits a logarithmic characteristic that when placed in the feedback loop of an op-amp produces a logarithmic response. This means the output voltage is a function of the logarithm of the input voltage as expressed by the following general equation. V out is equal to minus K ln times V in. They say where K is a constant and ln is the natural logarithm to the base E. Natural logarithm is the exponent to which the base E must be raised in order to equal a given quantity. Although we will use natural logarithms in the formulas in this section, each expression can be converted to a logarithm to the base 10 log 10 when using the relationship of ln x is equal to 2,3 log 10x. All right, then that brings us to basically this characteristic curve of a P-N junction. All right, you must be able to do this proof. I'm not going to go through it now, but you must be able to do this proof. And then we're going to start looking at our log amplifier. Our log amplifier is there on page 729. All right, what do we have in a log amplifier? We've got an op-amp, and we got a diode placed in my feedback loop. All right, a diode placed in my feedback loop. Now in this case, only in what must my input voltage be for that circuit to operate? My input voltage, what must it be, positive or negative? If I apply a negative input to my circuit, if I apply a negative input, will it work as a log amplifier, yes or no? No, it won't work as a log amplifier because the output will go positive. When the output goes positive, the diode is reverse biased, all right? And let's say I put a negative input so that my output go to, for example, to 5 volts. Will it work as a log amplifier? Your output can't go higher than 0.7. If your output go larger than 0.7, it won't operate as a log amplifier because we want to work on that curve. And when you go past 0.7 volts, it goes straight up and it won't work as a log amplifier. All right. All right, let's have a look at this analysis. They say VR is equal to minus VF, all right? And we can say IF is equal to IN. And then when we put it into that equation, I can say IF is equal to IN is equal to VIN divided by RIN, because my current there will be determined because that point will be at virtual earth. That's why I can state that my input current is going to be the input voltage divided by the resistance, all right? And that will also be equal to my forward current, all right? It will be equal to IF, the forward current of the diode. Now they say substituting for VF into the formula, then I can say VR is equal to minus K times T divided by Q, ln of Vin divided by IR times R1. And then they give us the term, they say Q times T, K times T divided by Q is a constant equal to approximately 25 millivolts at 25 degrees Celsius. Right, where did you use that 25 millivolt previously? Where did you use 25 volts previously in your course? By? When we calculate RE accent, all right, you remember RE accent that you use in the amplifier circuits, all right? RE accent was also equal to 25 millivolts divided by IE, because we also got a PN junction there. That is exactly the same, 25 millivolts. Then I can say VR is approximately equal to minus 0,025, all right, that's 25 millivolts, ln of Vin divided by IR times R1, all right. That is for the output of that circuit. Now let's quickly have a look at the example. When you look at this example, example 14.8, they say determine the output voltage for a log amplifier in figure 14.31. Assume IR is equal to 50 nanoamps. That IR is my reverse or my leakage current, all right? They give us the input is 2 volts positive. That means the output will go negative. That means the circuit can work as a log amplifier. Let's calculate the output. Right, VR is equal to minus 0,025 volts, ln Vin divided by IR times R1. And we work that out, we get a value of minus 0,15. All right, minus 0,15 volts. That means we're a lot away of 0.7 volts. That means it will still work as a log amplifier. All right. We can also place, also for a log amplifier, we can place a bipolar junction transistor in the feedback circuit, all right? And then it can also operate as a log amplifier. The formula will be a little bit different. Let's quickly have a look at the formula for this circuit. All right, they state VR is equal to minus RF times IC, because that's the current that's going to flow there. Then I can say IC is IEBO. What is IEBO? What emitter base current? I talk about IEBO. What emitter base current is that? Anybody? Electronics 2. We go back to electronics 2. What is IEBO? That is my leakage current. That is my leakage current or my reverse current. That's why they call it IEBO. All right. That's my leakage current. Same as my reverse current or my leakage current in a diode. All right. Now we can substitute that into for V out. Then you can say V out is equal to minus RF IEBO e to the power Q times VBE divided by KT. Now they say, as you can see, V in is equal to VBE. All right? And then we can say V out is equal to minus RF IEBO Q times V in divided by KT. The exponential term can be expressed as an anti-logarithm as follows. Then we can say V out is equal to minus RF IEBO anti-log of V in times Q divided by KT. All right, that KT divided by Q is also approximately 25 millivolts, exactly the same as previously mentioned. Then we can say V out is equal to minus RF IEBO anti-log of V in divided by 25 millivolt. Oh, here we are on the wrong circuit there. All right, this was the anti-lock, not the lock, the anti-lock. Because in the case of the anti-lock, what do? We will have the transistor in front. All right, we will have the transistor in front. In the case of the log amplifier, where we use the transistor, let's just go back to that. They will have the transistor in the feedback loop. All right. You can see where's my transistor now. My transistor is in my feedback loop. And again, IEBO is my leakage currents already mentioned. IC and IN, what can I say about IC and IN? They're going to be equal. All right. IC and IN can be equal. And then we can say, they say where IBO is the emitted to base leakage current. There they also tell you what's IEBO is the emitted to base leakage current. And then we can say VR is equal to minus 0,025 volts ln of V in divided by IEBO divided by R1. All right, let's have a look at this example because we're going to look at this answer a little bit later. We look at this, if we go and get the lock output here, they say what is V out for a transistor lock amplifier with V in is 3 volts, R1 is equal to 68 kilo ohms, assume IEBO to equal to 40 nanoamps. Your leakage current will always be very small. Now when we look at this, we'll find when we work it out, we get an output of minus 175.1 millivolts. All right. That is a log of this voltage of 3 volts, all right. Now, when we're going to look at the anti-lock amplifier, we're going to put that in and we'll see we'll get exactly the same answer out. Now, let's go and look at example 14.10. They state here, find the anti-lock in figure 14.34, find the output voltage, assume IEBO is equal to 40 nanoamps. But now, what is my input here? 175.1 millivolt. That means now we're going to get the anti-lock of that. If you got the anti-lock, what should we get? We should get 3 again. Let's go and have a look. All right. Now we go and look at that. VR is equal to minus RF IEBO anti-lock of V in divided by 25 millivolts. Now when we put that 175.1 millivolt in, what is my output? 3 volts, minus 3, all right. You with me? That means it works 100% correct. Now this is one of the main applications of log amplifiers, signal compression. let's quickly look at this signal compression. Now, if we go and look at a linear signal compression, that means linear means I'm going to compress everything of that signal exactly the same, all right? Now, let's say you got something like that. You put it through a linear signal compression. What? The large amount and the small amount will be compressed exactly with the same value, all right? Let's say my compression is 10 or my compression is 100. That means I'm going to make that signal 100 times smaller. But when it's linear, this large type and the small type, everything will be 100 times smaller, all right? And now you can see this information. They say this portion of the signal may be lost when compressed to a very small amplitude. You see, you will lose that information. But when I'm going to make use of a logarithmic signal compression, what will happen? It will compress a large part much more than the small part, all right? And that means then that information is not going to be lost. You with me? That will happen in the case of a logarithmic signal compression. That's the big difference between linear and a logarithmic compression. Any questions? All right, 14.5.
That compression, so is it only for analog signals?
That will be for analog signals. All right, converters and other op-amp circuits. All right, here we're going to look at a few op-amp circuits, for different op-amp circuits that we can use. The first one is basically a constant current source. A constant current source. That means if I vary my load, see here, I vary the load, that current is going to stay constant. All right, up to a certain stage. If you made your load resistance very high resistance, the op-amp, all right, if the op-amp had infinite supply voltage, then it will work. But it can only do it in certain area. Now, how does this circuit work? We know that point is at virtual earth. That means this I in will be determined by what? V in divided by R in. All right. V in divided by R in will give me I in. But what can I say about I in and IL? They're going to be equal. All right. That means if I put a short circuit here, that current and that current will be the same. All right. And then if I increase RL, increase the resistance value, the current will still stay the same, up to a certain point, but it will give me a constant current. That's why they say a constant current. But remember, you can't make that too high. If you make it too high, you will reach a certain point where the op-amp will saturate, all right, and it won't be able to keep the current constant. Any questions? Any questions? All right, the next one is a current to voltage converter. Current to voltage. All right, if we have a look here. Here I got an input current, all right. That will give me a certain output voltage, or the output voltage will be determined by RF times I in, all right. Because that current and that current is going to be the same. Now, what do they have here? They have a light dependent resistor, a LDR there, light dependent resistor. Now, what happens if the light intensity varies? The resistance will also vary, and that will give me a variation in current that will be converted basically to an output voltage. All right, that's why they say it's a current to voltage converter. All right. Input current, output voltage. Any questions? The next circuit, what do we have there? All right. If I look there, what will I have there? I got an input voltage, all right. Due to the input voltage, I will have a certain current that's going to flow in the circuit, all right. And that, if I measure across that RL, it will convert it to a voltage. Because if I take current, multiply by resistance, what do I get? I'll get voltage. That's why they say it's a voltage to current converter. Input is voltage, the output current. Yes?
Does that circuit, the voltage to current converter, does that mean that IL is equal to I1 because they are in series?
Yes, because there, what is flowing in there? Very high input impedance. Is there any current flowing in there? That means IL and I1 is equal. All right. There will be a minute current flowing in there, but it is neglectable. All right. Because what does the op-amp always try to do? Exactly the same as previously mentioned. If I put 5 volts there, what will the voltage be there? 5 volts. Aye. Start getting clever, eh? Clever for the first test. Huh? All right, the last one, a peak detector. All right, the peak detector. Why do they call it a peak detector? If I apply, what input should we apply here? No, what? Positive or negative? If I apply positive, where will the output go? Negative, will it work? Think a little bit, will it work? If I apply positive here, where will the output go? Negative, all right? Will the diode be forward biased or reverse biased? It will reverse biased. When it's reverse biased, will it work? No. That means I will apply, when I apply a negative, where will the output go? Positive, all right. That means it will only work for positive, when I got a positive input, so that when I got a negative input, so the output goes positive, all right.
Isn't it that another inverter says?
What?
Isn't it that another inverter?
Oh, sorry, I'm talking nonsense. Sorry, I'm talking nonsense. Hey, there's somebody that's awake here. That is a non-inverting input. What must I apply? I must apply positive. So the output go positive. All right, because when it goes positive, the diode's going to be forward biased. And then if there's a high peak that will occur, what will happen? It will go through a diode forward biased, it will charge the capacitor positive, negative, and that charge will stay on the capacitor, right? You with me? The input, that is not a that's the non-inverting input we use. That means the input must be positive. All right. Now then, you can measure this peak, and if you want to reset, you just press the button there, and you will discharge the capacitor. I would rather put a resistor in there so that you don't create a short circuit, so that you can limit the current a little bit. All right. You with me? That is the peak detector. Any questions? No questions. All right, that is the end of this chapter. You can do the problems, the back of the chapter. We finish with chapter 14.